to Dr. Sohaila. My name is Lee Hong Si, and today I'll be demonstrating the logic circuit that my group developed for the group project for digital electronic systems. So the circuit we developed is a classroom attendance monitoring system that checks a student's attendance whether they are on time or not and marks them as present, late, or absent. So first let us have a look at the inputs. First we have E, which stands for entry detection, and it produces a high output when a system, for example a sensor, it manages to detect a student's entry into the classroom. And V, it stands for ID verification, and it produces a high output when the student successfully verifies or scan its student card. T is on time, and it produces a high output if E and V are both high outputs. And now let's have a look at the outputs. First we have P, which stands for present, and it produces a high output only when E, V, and T are all high. L is late, which produces high when E and V are 1, but T is 0, which means the student is not on time. A is absent, which occurs when E or V, either one is a low output 0, and it does not depend on T, which we'll see on this, which we can see on the logic circuit. So P, the Boolean expression for P will be E and V and T, as we can see here, as all three inputs are connected to this AND gate. L, late, is E and V and T bar, so as we can see here, and T is connected to an inverter. And lastly is A, which is connected to E and V, which are also connected to inverters, and lastly an OR gates, and this output does not depend on T. So now let's have a look at the timing diagram, or the waveform based on the logic circuit earlier. So the shape of this timing diagram is based on the truth table developed. So doctor can refer to the truth table. And now let's have a look at the output produced by simulating it. So here is our waveform output. As we can see, P is only high when E and V and T, all three are high as well, and absent is entirely high for the first few microseconds when either E or V is 0, and a absent is low only when both E and V are high. And as for late L, it is 1 high when E and V are 1 and T is 0. So now let's have a look at the NAND configuration for the attendance monitor system. So to gain the logic circuit for NAND configuration, we simply have to double bar the original expression and perform De Morgan's theorem once to gain an SOP expression, so we can properly use NAND gates. And I forgot to mention earlier, to gain the original Boolean expression, we simply just have to loop the ones in the K-map to gain the SOP expression. So let's have a look at this logic circuit. So the inputs stay the same and output as well. However, we switch every basic gates with NAND gates. So first of all, for output P, it was originally one single AND gate, and now it's replaced by two NAND gates. The first NAND gate is connected to all three inputs, and it goes through involution again to cancel the inversion, to gain a more a quote-unquote positive output. And then for L, the NOT gate is also replaced by a NAND gate by connecting T to this NAND gate twice, and then the three EVT are connected to this NAND gate, and finally it goes through involution again to produce output L. As for A, the two NOT gates which was connected to E and V are now replaced by one single NAND gate, which can be proven via De Morgan's theorem. And now let's have a look at the waveform. So the shape of the timing diagram doesn't change as the input and output are essentially the same, even though the logic circuit is entirely different now. But like I said, it will be the same due to the NAND the NAND Boolean expression is derived from the original expression, the original SOP expression. So as you can see here, the output is exactly the same from before, where present is only high when EV and T are high, and so on. And that's all from me. Thank you for listening.